High-temperature H₂S and H₂ corrosion or sulfidation, understanding chemical degradation in industrial environments. High-temperature H₂S or H₂ corrosion, commonly referred to as sulfidation, is a severe form of metal degradation that occurs in refining and petrochemical environments. This phenomenon typically begins at temperatures above 400 degrees Fahrenheit or 204 degrees Celsius and is most prevalent in hydroprocessing units such as hydrotreaters and hydrocrackers. The process involves sulfur compounds reacting with hydrogen to form hydrogen sulfide, H₂S, which aggressively attacks steel surfaces. The corrosion mechanism leads to the formation of iron sulfide scales that are brittle and prone to spalling, exposing fresh metal to further attack. This cycle accelerates metal loss and significantly reduces equipment life. The presence of hydrogen amplifies the corrosion rate, making it a critical concern for high-temperature operations. Understanding this corrosion type is essential for ensuring the integrity of refinery equipment and preventing catastrophic failures. The environment where high-temperature H₂S/H₂ corrosion occurs is typically hydrocarbon streams in refining and petrochemical units, including hydrodesulfurization and hydrocracking processes. These streams contain hydrogen sulfide and hydrogen, creating a highly reactive environment. The corrosion process starts above 400 degrees Fahrenheit 204 degrees Celsius and becomes more aggressive as temperatures increase. Mechanistically, sulfur reacts with metal surfaces to form iron sulfides such as Fe(S) and Fe3S4. These sulfide scales initially provide some protection but are brittle and tend to flake off under thermal and mechanical stresses, exposing fresh metal to further attack. Hydrogen accelerates this process by enhancing the chemical reactions and destabilizing protective layers. The damage caused is primarily uniform thinning of metal surfaces, which can lead to equipment rupture if not managed properly. Carbon steels and low-alloy steels are highly susceptible, while stainless steels with higher chromium content, 9 to 12% Cr, offer better resistance. The mechanism of high-temperature H₂S or H₂ corrosion involves a series of chemical reactions between sulfur compounds and metal surfaces. Initially, sulfur reacts with iron to form iron sulfide scales, such as Fe(S) and Fe3S4. These scales act as a temporary barrier, slowing down further corrosion. However, the presence of hydrogen significantly accelerates the breakdown of these scales. Hydrogen promotes the catalytic decomposition of sulfur compounds, increasing the formation of H₂S and destabilizing the sulfide layer. As the scales become brittle, they spall off due to thermal cycling and mechanical stresses, exposing fresh metal to corrosive agents. This continuous cycle of scale formation and spalling leads to rapid and uniform metal loss. The process is particularly aggressive in high-temperature zones and areas with turbulent flow, making it a major concern for hydroprocessing units. Hydrogen sulfide or H₂S in refining environments originates from multiple sources. Sulfur compounds present in crude oil, such as thiophenes and mercaptans, are converted to H₂S during hydroprocessing operations like hydrodesulfurization and hydrocracking. Additionally, microbial activity, particularly from sulfate-reducing bacteria, can produce H₂S in cooler sections of the process. At high temperatures, the decomposition of sulfur-containing compounds further contributes to H₂S formation. These sources collectively create a corrosive environment that, when combined with hydrogen, accelerates sulfidation. Understanding these origins is critical for implementing effective mitigation strategies, such as controlling sulfur levels in feedstock and optimizing process conditions to minimize H₂S generation. High-temperature H₂S or H₂ corrosion primarily causes uniform metal thinning, which can compromise the structural integrity of critical equipment. This type of damage is particularly dangerous because it may not produce visible signs until significant metal loss has occurred, increasing the risk of sudden equipment rupture. Carbon steels and low-alloy steels are highly vulnerable to sulfidation, while stainless steels with higher chromium content, such as 304H, 310, and CRMO alloys like P91, exhibit better resistance. Chromium enhances the formation of stable sulfide scales that are less prone to spalling, providing improved protection against corrosion. Selecting appropriate materials for high-temperature environments is essential to prevent catastrophic failures and ensure long-term reliability of refinery operations. Preventing high-temperature H₂S or H₂ corrosion requires a combination of material selection, process control, and monitoring. Using high chromium and chromium-molybdenum alloys, such as 304H, 310, and P91, provides enhanced resistance to sulfidation. These materials form more stable sulfide scales that resist spalling, reducing metal loss. Process control measures include managing operating temperatures, controlling sulfur and H₂S levels, and optimizing hydrogen partial pressure to minimize corrosion rates. Regular monitoring through techniques like ultrasonic testing is essential for detecting early signs of metal thinning and preventing unexpected failures. Advanced software tools, such as S-Compass, can assist in predicting corrosion behavior and selecting suitable materials for specific operating conditions. Implementing these strategies ensures the safe and efficient operation of hydroprocessing units. High-temperature H₂S H₂ corrosion is a critical issue in refining and petrochemical industries, particularly in hydroprocessing units operating above 400 degrees Fahrenheit 204 degrees Celsius. The combined presence of sulfur compounds and hydrogen creates an environment that accelerates sulfidation, leading to uniform metal loss and potential equipment failure. Effective mitigation requires selecting corrosion-resistant materials, such as high chromium alloys, and implementing robust process control measures to manage temperature and sulfur levels. Regular monitoring and predictive tools further enhance corrosion management, ensuring operational safety and reliability. By understanding the mechanisms, sources, and preventive strategies, refineries can minimize the risks associated with sulfidation and maintain the integrity of their assets.